All right, and get the, oh, so it's not showing that I can share the PowerPoint, huh? One sec. Let me try to reload PowerPoint, see if we can share this. All right, so it looks like I can't just share PowerPoint for some reason today. So I'm gonna be sharing my whole screen with you. One sec. Okay, so that is the wrong PowerPoint. All right, there we go. Just keep in mind, since I am sharing my whole screen here, I'm not sure if you send me a private message. When I pull up the chat message, it will probably show to everybody. So just keep that aware. Any message you send me, if I look at it, people probably see who sent it just for today, because for some reason I can't just share PowerPoint. So let's conduct a little business here at the beginning of class. Test next week, Wednesday. The lecture we go over today should be the last material on the test, unless, we don't finish everything, and then we will finish it on Friday, and so that will still be on test one. Test one will be on Blackboard, so it'll be under course content. You will be recorded while you take this test. So I will be using a service called ProctorU. And basically what will happen is you need to show your ID, and any ID, any government ID. And it will record you while you take the test. And I also have the option of jumping in while you're taking the test, and you won't know that I'm watching you, which is a little weird, but I could be watching you while you take the test. Basically, you need to be in a room by yourself, that's free of stuff. For the test, I will give you a periodic table to use, so you cannot use your own. I will give you an equation sheet, so you can't make your own equation sheet. And you'll have scratch paper to use. I'll put this up in the announcement section of Blackboard as well, just so it's there. One last thing, the best way to study and prepare for this test is to go back through all the problems we've done for test one. Make sure you know how to do everything. The way I make tests for Gen Chem is that I just go back to see what problems we've done, and I'll ask the same type of problems, right? So anything you see on the test, I have covered in one of these online lectures. I have shown you how to do it. So I expect you to be able to do it. So that's what I'll be testing you over. All right, so that's just a little business out of the way. So, and the way the test will work is that it will open at 12 a.m. and it will close on 12 p.m. on that Wednesday. So you will have all day to do the test whenever you want. But as soon as you open the test, a timer will start, and you have 1 hour to complete it as soon as you start it. So make sure you are, you set aside an hour where you won't be bothered or anything like that. All right, so now let's actually get on to material now. So what we need to talk about right now is composition of compounds. And we're going to talk about mass percent. And mass percent is simply looking at an element, or a compound rather, and seeing for a compound, what percentage of the weight of that compound is made from a particular element. So what I mean by that is, in this example here, we have H2O. And I'm asking, what percent of the mass of H2O is made out of hydrogen? Well, to do that, we use the equation shown here. Mass percent of element X equals, what is the mass of that element in 1 mole of the compound, divided by the mass of 1 mole of that compound multiplied by 100%. And so our example for water is, water has a molecular mass of 18.02 grams per mole. Again, we learned how to do that on Monday to find a compound and get the molecular mass. Hydrogen, if we look on the periodic table, has a weight of 1.01 grams per mole. Some periodic tables have 1.008, same thing. So the mass of hydrogen in water, we have 2 hydrogens, so we take 2 multiplied by the weight of hydrogen, divided by the total weight of water, which is 18.02, multiply this by 100%. And what we find out is that 11.2% of the mass of water is due to hydrogen. So that's all we're doing. Find the weight of a compound, find the weight of the elements in that compound, divide the two, multiply by 100% to find out mass percent. All right. So simple enough, even though it might have sounded confusing when you hear it, but the calculation itself is relatively simple. So you saw an example on the last slide. So what I want you to do is try A and B to see if you understand this. I want you to calculate the mass percent of magnesium in magnesium chloride. So the first thing you need to do there is actually figure out what is the chemical formula of magnesium chloride. And I want you to calculate the mass percent composition of carbon in C2H5Cl. So see if you can get those numbers for me. Yeah, that's what we'll start with. If you're confused, not quite sure what to do, as always, feel free to message me. Again, I have to share my whole screen today for some reason. So if you send me a private message, when I go to look at it, there's a possibility that everybody will see it because I'm screen sharing. So just keep that in mind. If you have something really private you want to talk to me about, email is probably going to be the best way to do that today. But yeah, let's get started on these calculations. So like I said, the first thing we need to do is figure out magnesium chloride. So this is a good refresher back from what we've been talking about the last couple of days. Look on our periodic table, magnesium's element 12. So magnesium, let me get my pen out. There we go. Magnesium has a +2 charge. Chlorine is a halogen. Halogens always have a -1 charge. So we would need to make a neutral compound. So it would be MgCl2. That's magnesium chloride, right? So now we have to calculate what is the mass of magnesium chloride. So we look at magnesium. It is 24.305 AMU or grams per mole. Chlorine is 35.453. And we have 2 chlorines, so we need to multiply this number by 2. And we add them together. So same calculation we did on Monday. And we get that the weight of magnesium chloride is 95.211 grams per mole. Now, I want the mass percent composition of magnesium. So the weight of magnesium in this compound for 1 mole, we only have 1 magnesium, so it is 24.305 divided by the total weight of our compound, 95.211, multiplied by 100%, and the weight composition of magnesium is 25.528%. Questions about A? So now that you see A, hopefully, if you weren't sure what to do, and for some reason you didn't ask me about it, hopefully now you do know what's going on here. So B, hopefully, will be relatively easy because I give you the formula right there, right? I don't ask you to make the formula. C2H5Cl. And always, so I'm just going to write down the steps to solving this problem. Step 1, what is mass of compound? Step 2, what is mass of element in compound? Step 3, divide step 2 by step 1. Right, so that's basically all we're doing here. And multiply by 100. Whoops. So we look on our periodic table. Carbon has a weight of 12.011, and we have 2 of those. So 2, so this is carbon. 2 multiplied by 12.011 plus, now we have hydrogen. We have 5 hydrogens multiplied by the weight of hydrogen, 1.008, plus, now we have chlorine. We have 1 chlorine multiplied by 35.453. So we do that, and we find that the weight of our compound here is 64.515. And this is either grams per mole or AMU. Do we always provide composition, or do we need to know the common substances? I'm not going to ask you to memorize every single substance in the world. You should be able to look at the word magnesium chloride and base what we did on Friday and last week. I do expect people to be able to read the word magnesium chloride and know that's MgCl2. That is definitely something you need to know. Basically, at this point, what we went over in the whole naming scheme, I should be able to give you almost every simple compound in the universe, and you can tell me what it's made out of. As long as I give you the scientific name of it, you should be able to figure it out. I won't give you anything super complicated, but yeah. Okay. What is the mass of the element in the compound? Well, my handwriting is garbage. So we care about carbon. We have 2 of those, and the weight's 12.01. So that's simply 2 times 12.011, right? And I didn't actually do that, but what is that? 24.022. It should be that number. Take 2 divided by 1, multiply by 100. So 24.022 divided by, so that's the top is the weight of carbon, the bottom is the weight of my compound, 64.515, multiplied by 100%, and that is equal to 37.235%. So the weight of C2H5Cl, the weight of that due to carbon, is 37%. What did I say the answer to B was? 37.235%. Any questions about calculating mass percent? How would we round on the exam? I think on the periodic table, yeah, each one has 5 digits, so it'd be 5 digits. So when finding carbon in C2H5Cl, we count the number of carbons or just 1 carbon? You need to count the number of carbons because the question is, in this compound, what percentage of the total weight is due to carbon? So that depends on how many carbons we have in the compound. Does it matter if we round the element before calculating it? It probably shouldn't, but if you're looking a number up on a periodic table, you wouldn't round anything. Do we count carbon at 12.01? We have 2 carbons, so it's 2 times 12.01. My periodic table has it 12.011. That's why I have the extra 1 there. And the periodic table I'm looking at will probably be the one I give you. So just read whatever numbers on that periodic table and use that moving forward. Any other questions? Give you a minute while I do another little doodle. Chemistry is fun, said nobody ever. All right. So are we going to get a formula sheet? Yes, I will give you a formula sheet. You are not allowed to write on it, but I will show you what it is before the day of the test. But I will put it on Blackboard. And I believe the way that it works is that you have to show this formula sheet like to the camera to verify it is the formula sheet and like you didn't write on it. Can I post the periodic table? Sure. The periodic table I'm using is like just about the same as any periodic table you'll find. But if you just want to see it, that's not a problem. Okay, so let me clear this and let's move on to the PowerPoint for actually today. So let me get out of here. Let me switch to the 16th. All right. Let me get my notes switched over. So this slide that you're seeing should look familiar. We talked about it already, how we can talk about compounds in different types of formulas. We can have a molecular formula that has all the elements in it, like 4 carbons, 10 hydrogens. Empirical formula, where we just divide everything by the common denominator, I believe. I forget those terms. Common factor, yeah, the greatest common factor, there we go. So C4H10, the greatest common factor there is a 2. Divide everything by 2, you get C2H5. Or this structural formula on the bottom here. If I print the formula sheet, can I write on my copy? You cannot write on your copy until the test begins. No. You need to print out your formula sheet, but you are not allowed to write on it until you start the test. If any writing on the formula sheet is done before the test starts, that's basically an automatic 0. So don't do it. Is our calculator and scratch sheet going to be digital? No, your calculator will be in your hands. Your scratch sheet, you will provide like a regular sized piece of paper. I don't want any jokesters of, you said we get 1 piece, so I've got this whole huge piece of paper that's like 5 feet by 5 feet. Regular size A1 paper. You are going to need to print out the formula sheet because the software we're using knows when you open up other stuff on your computer. So yeah, don't get dinged for that. So you need to print out the formula sheet, and I'll have that up. I'll probably work on it on Thursday. So moving on to chemistry, not just chemistry tests. We're going to figure out how to find an empirical formula, right? So let's say you did an experiment, and the experiment I'm talking about is called bomb calorimetry, more or less, or mass spectrometry. Yeah, it's more like mass spectrometry now that I think about it. So let's say you have a compound, and you don't know what that compound is, but you blow it up. And when you blow it up, you find that you have for example, you have 50 grams of element A, 30 grams of element B, and 10 grams of element C. And we want to figure out what is the empirical formula for this. Well, the first thing that you should do, actually, let me say 20 grams of C. The first thing you should do is to convert your percentages into grams. So I kind of got ahead of myself, but let's say you did an experiment and 50% of their compound that you're exploring is made out of element A, 30% is element B, 20% is element C. Then you convert those into grams. So you have 50 grams of A, 30 grams of B, 20 grams of C. After you convert from grams, you need to convert to moles using your periodic table. So you'd look up element A and you'd find its molecular weight, right? And so you would say, if I have 50 grams of A, how many moles of that? You then write a formula using moles as a subscript. So let's say by doing this, you find out you have like 2 moles of A, I don't know, 8 moles of B, and 4 moles of C, right? So step 3, you would write your moles as a subscript. So you do A2, B8, C4, right? And that's just by using the periodic table there. Let me get to these questions. Is the periodic table going to include stuff like carbonate or phosphate, for instance? No. Kevin, so that's already been taken care of, so you don't need to worry about that. Once you have the formula as well as the subscript, you divide all numbers by the smallest number you have. The smallest number I have is 2. So you divide everything by 2. So that would be 2 divided by 2 is 1, so A. 8 divided by 2 is B4. 4 divided by 2 is 2, so that would be 2. So A, B4, C2. If our whole numbers, if our subscripts were not whole numbers, we multiply all the subscripts by a small whole number. So here in my example, everything's a whole number, so we don't need to do that. But let's just say for an example, I got, and I hope this will work out, I got A2, B9, C4. So let's say that's what I got for step 3 instead, and I divide everything by 2. I would get A, B 4.5, and C 2. Then you multiply everything by a small number. So multiply everything by 2, multiply everything by 3, multiply everything by 4 until you get to a whole number. Here, my example wasn't so great because I was thinking off the top of my head, but if you multiply by everything by 2, you'd get back to your original thing, and that would be your empirical formula there. But those are the steps for empirical formula, and I'm sure that was just clear as mud as what to do. So the best way to learn this is to actually do a little bit of practice about what is going on here. What if you get a subscript of 1.18 or 1.19? Is there an easier way to get the whole number instead of constantly multiplying? There is not an easier way. And you probably, if you get like 1.18 or 1.19, I would just round that up to 1.2 and you multiply everything by 5. Then that comes out to 6. So that would be a whole number. Sometimes when you do this, that will happen where you get like 3.98. 3.97. Then you just round up to 4. Sometimes, because in experiments in real life, not everything's neat. You're going to have some variance. And so if you did an experiment and you found out, oh, I have 3.98 moles of carbon, you can't have 3.98 atoms in a compound. And that's kind of what we're doing here. We're finding out in a molecule how many atoms are involved in that molecule. You can't have like a point of an atom. You can't have 0.5 of an atom. You can't have 0.98 of an atom. The atom's either there or it's not. So there you just round up. So if it's 0.9 something, less than 0.1, I can usually round up or round down to get the atom. But in the examples that we do, we're probably not going to run into that issue all that much. Always round up? No. If it's 3.1, you do not round up to 4. You round down to 3. Those would be like the only cases. This is less than 0.1 or greater than 0.9 is when you would do rounding. Anything else, you would do multiplication. But enough of me babbling about that. Let's try it. I give you a compound. I hand it to you. You blow it up using fancy machines, and you find out that that compound was 40% carbon, 53.29% oxygen, and 6.71% hydrogen. I tasked you to give me the empirical formula. To make your life easier, I give you the steps of doing that here. Note that this question is fair game for the test next week, and I will not be as nice as giving you the steps. But if you need the steps here, there they are for you. So let's see if we can figure out the empirical formula for this compound. So hopefully we were all able to do step 1. So 40% carbon, 40% is 40 grams, 40.00 grams. Carbon is 53.29 grams. Not carbon, oxygen. Hydrogen, 6.71 grams. It's on the formula sheet, is it going to have the rules for naming compounds? No, it is not. It's a molecular mass for Avogadro's number. No, Avogadro's number and molecular mass are two different ideas. Avogadro's number, not avocados, although that sounds way more delicious. Avogadro's number is how many atoms are in a mole. Molecular mass is something you find off the periodic table for each element. It is CH2O. Avogadro's number, how many avocados fall from a tree in a given day? That's food chemistry. Okay, so we convert our percentages into grams. Convert your grams into moles using molecular mass. So we go to carbon. And carbon's weight is 12.01. So carbon, 12.01 grams per mole. If we have 40.00 grams of carbon and as a molecular weight of 12.01 grams for 1 mole, hey, it's a conversion. You know those conversions we talked about in week 1, how I said we're going to do a ton of conversions? Welcome to chemistry. So we take our 40 grams divided by 12.01. That's 3.33 moles. So our compound has 3.33 moles of carbon. Oxygen. We have 53.29 grams of oxygen. On the periodic table, oxygen has a weight of 16 or 15.999 grams for 1 mole. And when we do that, hey, we have 3.33 moles of oxygen. Hydrogen. So we have 6.71 grams of hydrogen. Periodic table, 1.008, whoops, 1.008 grams for 1 mole. And we have 6.66 moles of hydrogen. So using the periodic table, we can convert our grams into moles. Yes, you need to know how to know the rules for naming on the test. You are definitely going to see questions where I just say, name this element, or here's an element. Here's the name of an element, give me the formula. 100%. Okay, so we have moles. Now I need to write a formula using moles as subscripts. So I have carbon, 3.33. Oxygen, 3.33. Hydrogen, 6.66. All right, divide all numbers by the smallest number. The smallest number here is 3.33. So divide everything by 3.33. We get carbon, 1. So remember, if it's a 1, you don't write the 1. You just leave it as carbon. Carbon, oxygen, H2. So we know from our formula, from our empirical formula, in our compound, whatever our compound is, the ratio of elements is 1 carbon to 1 oxygen to 2 hydrogens. Now, you'd have to do more experiments to actually know what the molecular formula is, but just doing this experiment where you blow it up and just weight the various elements, we know 1 carbon to 1 oxygen to 2 hydrogens. And since I know what this element is, this would be glucose, because I made up this question. To sum, you don't sum anything, right? You convert the grams, the moles for each element. then you write down a formula using your moles as subscripts. So we had 3.33 moles of carbon, so it's carbon 3.33. 3.33 moles of oxygen, so oxygen 3.33. 6.66 moles of hydrogen, hydrogen 6.66. You take all those moles and you divide by whatever the smallest number of moles is in all of them. Our smallest number was 3.33. So I divide every single number I got by 3.33. At no time are we really adding anything there. Did you write CH2O backwards instead of COH2? Well, I get that wrong on the exam. Yes, you wrote backwards. No, it's not wrong. You could write H2CO. I mean, to a chemist, that's backwards, because what you're saying when you write it like that is that those hydrogens are acidic. And since I know what this compound is, that's not correct. But you don't know what the compound is, so it doesn't matter which order you write them in. You could write OCH2 or OH2C. That's all technically correct, even though to a chemist it's backwards to do that, but it's correct, right? Because all I'm asking, what I would get at with this question is, do you understand what's going on here? I'm not asking, do you know intuitively which order to put elements? I'm not interested in that. I'm interested in, can you do this math? Can you, oh, you cannot use your notes on the test. I will give you an equation sheet and a periodic table, and you can have blank pieces of paper. You cannot use anything else other than a calculator and a pencil. No notes. Any questions about this? How many questions on the test? I don't know, haven't made it. Test is next week, so I will be making it this week and the next. Generally, since everybody's asking about the test, generally my test lengths, 80% of you will be done on time, 20% of you won't be done on time. But I don't know if I don't think that's due to the test being too long, because generally when I make the test and then I take the test and I time myself how long it takes me to do it. And usually I aim for taking me no longer than 6 minutes, 6 to 7 minutes, because I figure if it takes me 10 minutes to do the test, no way you're going to do it in an hour, right? If it takes me 6 minutes to do the test, the majority of you could do it in an hour. I basically take my time and multiply it by 10. I figure I'm 10 times faster than people here. So that's a rough estimate to know, how long a test will take. What takes me a minute probably will take other people 10 minutes. So that's my rough rule of thumb. What kind of calculator do you need? I've been using TI 84 plus. That's fine. TI 84 plus. You should be fine. One piece of scratch paper. I think I'm gonna do 2 pieces on like front and back, because I don't care if you use scratch paper to do calculations. If you're studying in, well, we've had a month, right? Plenty of time to be studying this. If you've waited to cram, then yes, you should be a little bit fearful, because this is a lot of material to cover in 1 week to cram. If you've been stretching out your studying, like I've been suggesting and hoping people have been doing, no fear. If you understand all the questions we've been doing, no fear. I have a TI Inspire, that's fine. Professor, can we meet after class? You are named iPhone, so I'm not sure who that is. But anyways, I need to move on, because this stuff's on the test. Okay, so I think I sent you an invite over Zoom then, so check your email. Okay, balancing equations. So here, we don't really do math. Well, we kind of do math, but it's addition. Here, we're going to learn how to look at a chemical equation and balance it. So what is a chemical equation? So chemical equations are written in the form showed here. A plus B goes to C plus D. Here I'm saying I'm taking the elements A and B and combining them in such a way that I make elements C and D. Everything on the left side of the arrow are reactants. So that's what's reacting. Everything on the right arrow are my products. That's what I'm producing. Note, due to the first law that matter can't be created or destroyed, energy can't be created or destroyed, it can only change shapes, the law of conservation of mass, we cannot destroy atoms. We are not doing nuclear chemistry. I believe at the very end of Gen Chem 1 or Gen Chem 2, I forget which, we talk about nuclear chemistry and how you can destroy atoms and make an atomic bomb. We're not there yet. So we're going to say we cannot destroy atoms in regular chemistry. So when making chemical equations, we have to ensure that the number of atoms that go into the reaction equal the number of atoms coming out of the reaction. We can't gain new atoms. We can't destroy atoms. It's a scale. The left-hand side and the right-hand side of the arrow have to be equal when it comes to number of atoms. This is called balancing a chemical equation, like a scale. So I will show you how to do A. Then I'll let you try B, C, and D. And this will probably be the last thing that we do. Okay. So A, we have C5H12 plus O2 going to CO2 plus H2O. So this is a combustion reaction. We're taking pentane and we are lighting it on fire to make carbon dioxide and water. Fun fact, when you burn anything, you're always going to get carbon dioxide and water as your products. And you need oxygen and you need carbon and hydrogen as well. So burn stuff, you need carbon, hydrogen, and oxygen. All right, so let's take a look at this. The first thing I do is just simply write down what elements are in my equation. So I have carbon, I have hydrogen, I have oxygen. Those are the only three elements in my equation, right? Then I draw lines and I draw a big line down the center. The left-hand side are my reactants. And moving forward, I'll just put an R. The right-hand side are my products. Moving forward, I'll probably just put a P. All right. The first thing you need to do is count up the number of atoms on each side of the equation. So on the left side of the arrow, I have 5 carbons. I have 12 hydrogens. I have 2 oxygens. On the right-hand side of the arrow, I have 1 carbon. I have 2 plus 1, 3 oxygens, 2 hydrogens. Your goal is to make the numbers on the left-hand side of this line and on the right-hand side to be exactly the same. All right. So the way I go about this is that I will pick an element that only appears in one compound on one side of the equation. So by that, I mean I can either pick between hydrogen or carbon. Hydrogen only appears in one compound on the left, one compound on the right. Carbon appears on one compound on the left, one compound on the right. I'm going to start with carbon. That's what I usually start with. If given a choice, I'll go with carbon. You could start with hydrogen and get the same answer if you wanted to. But carbon is easy to me because I have 5 carbons on the left, 1 carbon on the right. Well, I need to have 5 carbons on the right. So I just put a 5 in front of CO2, saying I have 5 molecules of CO2. Now I need to recount the number of carbons and oxygens on the right-hand side of my equation because I just changed the numbers. So now on the right-hand side, I have 5 carbons, right? 5 CO2, so 5 carbons. The number of oxygens. So I have 10 oxygens from CO2, 5 times O2, plus 1 oxygen from H2O. So in total, I have 11 oxygens, right? So my carbons are balanced. So I'm not going to try to touch any carbon compound moving forward because I have 5 carbons on the left, 5 carbons on the right. I'm good. Let's try the balanced hydrogen now, because that was the other compound that only appeared in one compound on each side, or the only element, rather. So 12 hydrogens on the left, 2 on the right. Put a 6 in front of that bad boy to get 12 hydrogens on the right. Now we need to recount the number of oxygens. So we have 6 oxygens from water, 10 oxygens from CO2, 6 plus 10 equals 16, right? So carbon balanced, hydrogen balanced. We just need to balance oxygens. 16 on the right, 2 on the left. If I put an 8, 8 times 2 is 16. If I put an 8 on the left, 8 times 2, like I just said, is 16. That's a balanced equation. So for every 1 mole of pentane that you combust, you need 8 moles of oxygen, or 8 molecules of oxygen. You'll create 5 molecules of CO2, or 5 moles of CO2, and 6 moles of H2O, or 6 molecules of H2O. And that is how you balance the equation. You set up a table like that, and you just see number of atoms on the left and right. And your whole goal is to try and make that ledger balanced. So looking at that example problem, questions. How did we get 11 for oxygen? So before I changed H2O into a 6, right? Before that was a 6, it was 5 CO2 and 1 H2O. So 5 times 2 oxygens is 10 oxygens from CO2, plus the 1 oxygen from H2O, that's 11. But this should be a 6, so let me undo that scribbling. There we go. So it's okay that you just change the number of oxygens. It's okay as long as I change them. So what I'm doing is I'm changing moles, right? So I take the moles in front, and I can change that as many times as I want, right? I can change that to any number I want in the universe. The only thing is you can never change the subscripts. When balancing an equation, for example, this CO2, I can't change that 2. That's set in stone. Do you have to stay balanced to the lowest increment possible? Yeah, so for example, technically it is balanced if you say 2, 16, 10, 12, but you have to divide everything by 2. You have to go to the lowest amount that you can. Can I do C real quick? Sure, I don't know how quick it will be, but so it is 1050, just FYI. So if you need to be somewhere else, this will be provided online, this recording. So will the exam contain everything up to balancing equations? It will contain balancing equations. It will contain what we did empirical. And let me just see what question 3 is really quick, and then I'll do C. It will do naming carbon compounds. Question 4 on this slide is the last thing that will be covered on the test. I'll cover that on Friday on test 1. But let me do C really quick here. Empirical from combustion, since we didn't do that in class, no. So let me do C real quick. So CaOH. P. So those are our 4 elements in C. Do my lines. Reactant, product. All right, so let's count. We have 1 calcium on the left, 3 on the right. Oxygen, we have 2 oxygens here, 4 oxygens there. So that's 6 on the left. On the right, we have 4 times 2 is 8, plus 1 is 9. Hope you remember the parentheses. We did that in class. Remember that we did a problem like how many atoms are in the parentheses? So let me just, even though I'm trying to do this quick, I'll take a time out to say, if you do not understand something that we've covered in a lecture, don't just let that slide and figure, I'm going to get it later. Because the thing with this class and science in general, everything that we cover, I'm going to just build on it, right? So if you don't understand the foundation, the tower will just collapse on you during test time, and it'll be painful. So make sure that we get what we cover in class, because I'm just going to keep building and building and building on those foundations. All right, so oxygen's 9. Hydrogen, 2 from the left plus 3 from H3PO4 is 5 on the left. On the right, we have, what, just 2? Yeah, just 2 from H2O. Phosphorus, 1 on the left and 2 on the right. All right, so that's our initial counting of the elements. So I would suggest that you either start with calcium or you start with phosphorus, right? Because calcium only appears on 1 compound on each side of the arrow. Phosphorus, P, only appears on 1 side on each side of the arrow. So those will be easy things to balance. So let's just start with calcium. Why not? 3 on the right, 1 on the left. Easy fix, put a 3 on the left. So now I have 3 calciums. Now I have to recount all my oxygens. So I have 3 times 2. So that compound is giving me 6 oxygens, plus 4 from H3PO4. So in total, I now have 10 oxygens. Hydrogen. So putting the 3 in front of calcium hydroxide, I now get 6 hydrogens from that compound, plus 3 that we had originally. 6 plus 3 is 9. Phosphate doesn't change because I didn't do anything to it. Calcium is now balanced. Let's move on to balancing phosphate. 1 on the left, 2 on the right. Easy change. Put a 2 in front of my phosphate. So phosphate went from 1 to 2, but now I have to recount hydrogen and oxygen, right? So putting the 2 in front of H3PO4, 2 times 3 is 6 hydrogens. 2 times 3 is 6 hydrogens from calcium hydroxide. That's 12 hydrogens, right? Now the oxygens. 2 times 4 for PO4. 2 times 4 is 8. So that's 8 oxygens. On the left, 3 times 2 is 6. So 8 plus 6 is 14 oxygens. All right. Calcium, phosphate balanced. Let's balance oxygens and hydrogens. 12 hydrogens on the left, 2 on the right. Let's put a 6 there and see where it gets us, because I'll balance my hydrogens. So on the right-hand side, I just changed hydrogen and oxygen, so that's all I care about. So we went from 2 to 6 times 2, 12 hydrogens. Now we have to count oxygens, right? 6 times 1 is 6 oxygens, plus 4 times 2 is 8. That's 8 oxygens. So we have 8 oxygens plus 6 oxygens. 8 plus 6 is 14. Everything's balanced. So your final balance equation is that 3 calcium hydroxides plus 2 phosphoric acids make calcium phosphate plus 6 water. So I did that probably a little bit fast, but like I said, all of this is always recorded and uploaded for you to follow online. It is very cool once you understand what's going on there. But if you have any questions about this, anything at all from this last month, can you believe we've been in class for like a month now? Please reach out to me. Reach out to our SI leader, Michael. If you saw my announcement between now and next week, Wednesday, if you meet with Michael, I'll give you extra credit. If you meet with him twice, I'll give you more extra credit. If you meet with him 3 times, I'm not going to give you more extra credit on top of that, but your grade will improve. So do seek him out. Otherwise, this will go online. I will get some water. And I will see everybody on Friday, where we'll finish off this this slideshow, and whatever is at the end of the slideshow is the end of test 1. Otherwise, take care, everybody.